Hey everybody, who's all here? If you're in the chat, feel free to say hi right now. I'm trying to get something working inside of R right here. It's so close. It's so close. It's like a 475, 320 crossover right here. So close. Let's check this out, see if Brian can get his crossover working. But if you're in the chat, ask questions. Let's go check this out. So I'm trying to get an app that's going to draw out the logistic curve repeatedly, and the expression is giving me some issues right here. So I'm looking at the curve function right now, seeing how it works. It says expression. The name of a function or a call or an expression written as a function. So should I just call it as a function? Should I just write it as a function where we'll have to evaluate the x? Yep. So yeah, cool. So maybe I should try, I might try something else different in a moment. But we have here, maybe I don't want to do it as expression. I should write function. I think that's how I make it into a function. So that's going to call it as a function. If you have questions, feel free to ask them. Ubot's awake and hanging out right now. Looks like I have a parentheses error over here. And we can see where our parentheses end. So that ends it. You can see it connects right there. So we're ending it. Should make that go away. Just a little parentheses error right there. Go away. Is it going to go away? Or maybe not. We'll just wait. What's it mad about? Oh, I don't have another parentheses. I am missing another parentheses. There we go. I didn't see that one right there. The EXP, is it fine? It's mad about that EXP. Why is it mad about that EXP? So I think it's like, it doesn't like it as a function. What's it saying over here? Unexpected token. Closing bracket. So we see right here. Let's go and see what we got right here. Well, this is the EXP. And that closes the EXP off. And then we go over here. And we close this. And then we close off the function. Then we close off the reactive. Weird. 1.8. Yeah, some 320. What did I do to this? I coded too much. It was working with the, here we'll do it in 2 seconds right here. As expression was working, but that's not the right thing. But the function, it doesn't like that. Can we do as function? There's no as function, right? As function. Well, last attempt right here at getting this working. Doesn't like it. I'll have to look into 2. So video where we do chapter 17. Yep, we've been doing that recently. A lot of the recent assignments, Demetrius, and we can do one. Ask away on it. Let's hop here. 1A2 for 320. Let's go do it. And Demetrius, ask any sort of question you want. Be like, hey, Brian, can you work this one? We'll do some chapter 17. But a lot of the recent videos have been doing chapter 17. So check those out. Lots of recent chapter 17. Let's go check out 1A2 for 320. I'll get that app to work eventually. All these different things. Let's go check it out. 1A2. Well, we did this one. Are you talking about this one right here? Is the strength of the relationship between last amount and recent average amount stronger for homeowners or non-homeowners? Is this the one, homeowners, you're talking about right here, Nathan? Is this the one you're talking about right here? I can bring up the... We did this one earlier, and we can discuss if you want. But is this the one you're talking about right here? 1A2. So we've got the code written right here for it. No worries, we got this. Let's go check it out. We've got the code written for it right here. We're going to visualize the model. Hey, Brian, can we do? Yes, of course, definitely. We'll do that one next right here. And Demetrius, drop a question in the chat, and we'll make sure we do it. So I want you to look right here and tell me, how can you tell which of these is stronger? What does it mean to have a stronger relationship, and how can you tell this from the output right here? So we're looking at the relationship of how much people spend, their last amount spent, by how much they've been spending recently. And we have homeowner yes and homeowner no. So how can we tell? And so why would you think that, Nathan? You are correct right there, but why would you think this if you look at it visually, and then when you look at the output right here, when we look at this right here, and now we have to know what a reference level is. No is the reference level right here. So with no being the reference level, why is this slope right here the slope for no? Well, because homeowner yes, and yep, the higher slope exactly. So the higher slope is right here, and the difference in the slopes is this much. So does that mean homeowner yes has a negative slope? Does like you can see it visually, but you see this coefficient right here for recent average amount with homeowner yes, the interaction. What does that mean when you look at it? That interaction right here means what? Like, what does that mean for the slope of homeowner yes? It's not negative. You can look at it and you can say, well, that's not a negative slope. So the homeowner yes line does not have a negative slope. What does it mean that it has a negative interaction? its slope is that much less. The slope for homeowner yes is that much less than the slope for homeowner no, so it's a decrease in the slope of 0.17. Awesome. Great job, Nathan, right there. Some 100 points. Is Mubot awake? Hopefully he is. And Demetrius, drop a question in the chat right there. Mubot is awake. Drop a question in the chat, and we'll do it. And for 3A, it's just be the p-value on this. Maybe. Maybe. What does that one say? You'll have to tell me what it says. The answer is maybe. What does that question say? I don't know what it says off the top of my head. So the answer right now is maybe. It's maybe until I learn what it says. And thank you for swinging by here. Ask those questions. We got one more question on deck. Demetrius, if you have one, let me know. And we'll do that question next here. And we can work whatever questions we want. We are nearing the end of materials for every class. Sad times. End of material. Craziness. Chapter 17 quiz. Was it newspaper headlines? Oh, wait, no, you said 19. Chapter 19, Demetrius has the next question, it looks like. Yeah, it'd be p-value, yep. Chapter 17, I don't have any knowledge on it currently. Can we do what the equation of chapter 17 is? Yeah, so we'll do one with an equation. Great question right there. We'll do one with an equation right here. After this question, I'll find an equation one, and we'll do one with the equations to practice it. Great question right there. Knowing the equations is very important, and we'll do that here next. Was it newspaper headlines? I think you said, Kayla. The question is newspaper headlines. Sunken ship. It's talking about the Titanic. Newspaper headlines. Almost to it. Newspaper headlines. Let's go check this out here with the newspaper headlines. Newspaper headlines. Oh, wrong button. So we got some newspaper headlines on whether people survived or did not survive on this ship. Now, what is the easiest way to remember the word that goes between these two? What word goes between your X and your Y variable? You're welcome, Kayla, anytime. So what's the easiest way to remember the null hypothesis here, which we don't use statistical notation for? So this is two categorical variables. We have whether somebody was alive or dead. We have whether they were male or female. And you would just say what between the two of those, which is, we'll look for something similar to that over there in the notes. But what would you say? Independent, boom. That's the null hypothesis. It's just that these two are independent of each other. Just connect this, that whether you lived is independent of being male or female. So that should be the null, and we are seeing that over here. They are independent, which actually, you know what? I think narrows it down. You gotta watch out, because independent would mean the same as no association. So this is a possible, let's be careful. Now to say they're dependent, let's see here. I'm a little bit worried. Survival was independent of somebody's gender on the ship. Oh, there is an association. Good right here. And there is no association. My Pearson. Oh, you see, I don't like the way they word this. Right? What are the null? Wow, they're just this question, now that I look at it. It's not that they're dependent is the null. It's not that there's an association is the null. And they're really doing some flip-flopping of the wording right here. There is an association between, yes. If they tell me I get this one wrong, I'm going to scream. And I'm going to write the publisher again. So, yeah, exactly. The null is that they're independent. And the alternative, random doorbell ring. 2 seconds here, everybody. Be right back. I think it was just an Amazon package, probably. Are all the conditions met? Condition number 1, you know it coming up right here. Condition number 1 is random. Condition number 2 is that they are less than 10% of all individuals, which, are these random people? And condition 3 is that we have categorical data, 2 groups or 2 categorical variables, which we do have right here, count data. And condition 4 is we have at least 5 expected cell counts. Now, you could calculate the expected cell counts, but by just looking at this, these are not expecteds. These are the actual observed counts. The smallest expected cell count would be females who were alive. It was horrible. That's the lowest expected cell count, and it'd be row total times column total over grand total. And as long as this is greater than or equal to 5, you are good. So let's go ahead and do the expected cell count here. Row total of 708 times column total of 529 divided by 2182. And that is the smallest expected cell count, and it is greater than 5. So yes, these are count data. The groups are independent, and the groups have at least 5 observations. So they're basically saying random right there. That's just like randomized, but and then they don't mention the less than 10%. I wish they did. Now, this is where it gets into where we need jump. So I would not solve this by hand unless you have to solve out all the expecteds and all the cell chi-squareds. This would be a lot of work right here. So right now, we're going to go here to the table. We're going to remove out all the notation we have written, and we're going to go to copy to clipboard. With copying to clipboard, we're going to click Command-C or Control-C. And then we're going to go down here to jump and open up a new data sheet. File, new data table. I'll pause right here. So we've just copied our data, go into jump anywhere inside of it, go up to the top. On a Mac, it'll be at the very top of the screen. And then file, new data table. With the new data table open, we're going to go here and go to edit and then paste with column names. Make sure I'm going to pause here too. Make sure you paste with the column names this time. Why? Because it had column names. So we're almost there. We have to do one more step. We have to go here to tables, and then we have to go to stack. We're going to double click both the male and female column, table stack, double click, pause right here. And this is going to take both those columns and stack them on top of each other so we can analyze somebody's gender versus whether they lived or died. And now we'll click OK, and we have our final table. Make sure it has the data as blue, and then you have male and female, and you have gender right here, or alive and dead as, it doesn't say alive or dead. You can change the status, but yeah, let's do that. Just double click it right here and go to status. Makes it a little bit easier right there. And we've got label and status, and we have the data right here. If you really want, if you can't get it in jump, you could always type these in: alive, alive, dead, dead, female, male, and then put the numbers associated with those groups. As in, there were 404 females who lived, 304 males who lived, 125 females who died, and a lot more males who died. I think we're going to see an association right here. So when we look at this, we go to Analyze Fit Y by X. Analyze Fit Y by X. And we're going to put the data into the frequency, which is how many individuals there are in each group. And then we're going to see if somebody's label, whatever they were, would explain whether they lived or died. And let's click OK. And you can definitely see more males died, as we saw down here when we looked at the data. Now, is this statistically significant? The answer is down here with the p-value, and it's ridiculous. This right here, the chi-squared test statistic, is the Pearson. And I do want to point out a few things. The Pearson chi-squared test statistic is found by adding up all the cell chi-squareds. The cell chi-squareds are basically how far off these numbers are from each other. So these are the cell chi-squareds. 314 plus 151 plus 100 plus 48 is going to equal 614. The Pearson has your p-value. The p-value tells us that this is statistically significant. And this is the chi-squared, which is like a t, a z, but it's what we use for this distribution. So how do we get these cell chi-squareds? I'm kind of reviewing a little bit here because we've already answered the questions for my Pearson assignment. But the cell chi-squareds would be found by using the observed minus expected squareds over expecteds. Let me write out that formula for you right here. The formula for a cell chi-squared is going to be, because this is on the test, observed minus expected squared over expected. So if you were to take any of these numbers, like the observed of 404 minus the expected of 171,646, square that difference so it's positive, and then divide by the expected, you can double check your work. And this is a really good thing to do to practice to make sure, okay, wait a minute. Could I find a cell chi-squared? Will this solve to 314.532? So 404 minus 171.646. And then we square that and we divide by 171.646. And that's it right there. If you look, we actually had that expected cell count on the screen because we had solved this previously by doing row total 529 times column total 708 divided by grand total 2182. to 2182, and that is going to be the expected, which is right here. Remember, the expected is probably the easiest equation to remember because it's always going to be row total times column total over grand total. So that's row total times column total over grand total, and you basically just point in on the cell you want to solve for. So by doing this, you're solving for females alive because you're taking the row total for females, the column total for alive, and using the grand total and finding out basically how many we would expect for females alive. This is once again the smallest, greater than 5 means we pass the condition. We were looking for this down here though, which is the chi-squared test statistic. And the chi-squared test statistic is going to be equal to 614.617. 614, 617, let's remember that. So 614, 617. And we go down here to 614, 617, which rounds up. And the p-value is about as zero can be. So we're going to reject the null for certain. So it's either A or C. Reject the null hypothesis. Reject the null hypothesis. There is weak evidence. No, there's strong evidence. To conclude an association. Too worried about this Pearson trickery right here. Oh, did we miss something? Oh. Are the conditions satisfied? Yes, because they are this. I think, Kayla, do you have any additional questions? Hopefully we've kind of solved this one out. Woo! I've been just like so worried lately. Like, I know all this, but my brain sometimes misses it. Sometimes it happens. We don't make mistakes here. We get everything right. Demetrius, we're going to do a chapter 17 question. Let's go do it. Wrong button. Let's do some chapter 17. I know I should never doubt myself. I'm just like, I clicked the button. Did I click the right one? It's so much easier when you get to interpret it. You're just like, oh, that p-value is ridiculous evidence. I mean, looking at the graphic, it's like, well, yeah, it's like males were way more likely to die. You can just see it visually. Go take a look at the visualization, and it's like, there is a ridiculously strong association right here. Males had a much higher probability of dying, and that probability is very unlikely by random chance, so we reject the null hypothesis. And then Pearson tries to trick me with some wording. Tricky, Pearson. Let's go do one of the ones with the equations from chapter 17 to solve out some math equations right here. Chapter 17 is all about those math equations. This assignment is due 2 days from now, and we'll be covering it in depth tomorrow. Kind of like that. I kind of like where we, not too long, because we want to make sure we cover it, and then we have time to review it. So very important right here. We won't do a jump one. Let's do one where we do the equations by hand. We did the drinking glass one yesterday, I think. I'm trying to find one we haven't done lately. Do people spend more at store A or store B? Let's do the store spending one. So I had a quick question about the project. If you wouldn't mind, I'm confused on the hypothesized value in sample C. Yeah, we'll go over that next, Ariel. Great question, Ariel. Next question right here. You got it. So do people spend more at store A or store B? So we have here what? 80 people went to store A. That's what that means. 77 people went to store B. The people at store A spent $42. The people at store B spent $50. And the variation, this would just tell you like how spread out their spending is, was 21. So there's more variation in what people spend in store A than there is in store B. They're pretty similar, but a little more variation. Yeah, that's awesome. Let's review. You're right. Great job. 100 points there, everybody. Chilling out here doing some work. And let's go ahead and run the equations on this. So let's go run some equations. Let's remove all this. And what we need to do is we need to find out, first the null hypothesis. And I think it's going to be a does not equals. So suppose the researchers collected asking, perhaps they spend, summarize this. Suppose researchers had tests that the means are equal. So the null hypothesis always has the equal sign. So there you don't get a hint on that. But since we're testing to see if they're equal, the alternative would be that there is a difference between the means. The null hypothesis being that the mean for store A, like in truth, people spend the same. There is no difference between what they spend in store A or store B. The null states that the true mean for A minus the true mean for what they spend at store B is equal to 0. There is no difference. The alternative would state that the true difference for what someone spends between A and B has a difference that is not equal to 0. So there we go with our null hypothesis. And now we need to write the test statistic. This is where a lot of the work is and where the errors can happen. So let's go ahead and write our equation right here first. The equation we are going to write is going to be, let's do it in a nice calming blue, is going to be y bar 1 minus y bar 2. We'll use 1 and 2 for A and B. And then we'll do over square root S sub 1 squared n sub 2 plus S sub 2 squared over n sub 2. You do get these equations on the test. And that is going to be equal to, we have here the mean for A. Let me make sure it's A minus B. It is. Good. Let's make sure we're doing it in the right order. And that means, I think I changed the thickness of this. Maybe that's not where we do it. All right, we'll keep doing it. And then we go right here and we have mean for 1, 42 minus 50. And that's going to be over square root of sample or standard deviation 21 squared over 80 plus 19 squared. That's standard deviation over 77. And we get a difference of -8 over the standard error. This is going to be the t. And let's solve it. 21 squared, we're going to solve it twice to make sure. Oh my gosh. 21 squared over 80, copy that. 19 squared over 77 plus the 2, square root 3.19. So now we take 42 minus 50. And that's a t-statistic of -2.5. A t-statistic of -2.5. And round to 2 decimals it is. So let's double check our work. And let's make sure we got it. 21 squared divided by 80. Copy that. 19 squared divided by 77. Add those two together. Square root that. 42 minus 50 divided by this. There we go. Make sure you put the negative because this is a negative difference. Very important right there. Now, this right here has to be brought over to a t distribution. So we know what the t-statistic is, and that's a pretty big value right there. That's a pretty big value. Let's go ahead and take a look right here. And let's bring up our t distribution and our t degrees of freedom. Now, this is, if you put in the wrong value into the t degrees of freedom, you have a bad time. Find that out the hard way, right? So we're going to go ahead and take this right here. I'll put a little chill music on, relax right here. We got our t-applet. Here's the t-applet. And then we need our degrees of freedom. I know, right? Sad times. Where's Mubot? Where's my degrees of freedom applet? Mubot, you want to tell me where that degrees of freedom applet is? Charlie Quick's degrees of freedom applet. One time they made it so Mubot couldn't post links. It was last semester. Every time he tried to post links, it would get like stopped by YouTube. It was like, this comment has been removed by like YouTube. So Mubot was like, it was a big bummer. But Mubot, we might have hit him too quick on those 2 links. He might have said, I'm on my cooldown. I can't do it. I think the sample sizes were 80 and 77 respectively. And so there's the sample sizes of 80 and 77 respectively. And then 21 and 19. We're just literally taking these numbers right here, getting the degrees of freedom. And the degrees of freedom, check, great job right there. Now we're going to go over here and we're going to put in the degrees of freedom into this applet. Now we take our t-statistic and do -2.50. And a very important part of this, can we run through? Yeah, we can do that. We got a question right before this, but you bet, Michaela, definitely. Michaela, sorry about that, Michaela. But with this right here, why are we doing the two-tailed test? One might be wondering, wait, Brian, how do I know to shade this to the right, to the left, or both tails? Why are we doing the two-tailed test? Why am I shading both tails of this? Why have I decided on this both tails thing right here? I'm not shading to the right, not shading to the left. It's the does not equals. The does not equals is the two-tailed. Remember, it points both ways, so we're doing the does not equals. Exactly. They said we're testing if it's equal, so the alternative is not equals, which is the two-tailed test shading. And the p-value here is 0.013. We're using an alpha of 0.10 for reasons, and that means we are going to reject the null, and there is evidence. The p-value here is low. Reject the null. There is evidence. Hold your breath. And we got that 100. Kayla. And so the reason, does that make sense, Demetrius? The reason we're using the two-tailed test is because we are doing the does not equals alternative. The alternative tells us what way we're shading the curve. If we had used the greater than test, like if this was the answer right here, which it's not, just pointing that out, we would shade to the right because the alternative points to the right. Great job, Demetrius. Now, this is not the answer. It's just if we had picked this alternative, we would shade this way. If you had picked this alternative, which you could, I'm not saying you should, but there's tests that do that, you would shade this way. So on the less than alternative, you shade to the left, And then on the does not equals alternative, you shade both sides, which will double this right here. When I click the two tails, you'll see this will double and go to the other side. And there's some decimals we don't see, but this is doubling it right here. So we've done it. We've done it. I think the next question was about the project, about a hypothesized value. Let's go talk about the project here with hypothesized value. Awesome. Some one sample Z right here. Let's go do this. One sample Z. Pulling up my project data right here. Let's go do some one sample Z talking about hypothesized values. Let's go take a look at those. Here we go. One sample Z time. So we're doing some one sample Z stuff right here. Now, one sample Z deals with proportions. And what are we dealing with proportions? Proportions are what types of variables. If you hear a proportion, you know condition 1's random, condition 2 is 10%, and then it's success failure because for the third condition, which we don't have to do conditions, but proportions are what kind of data, which we could do proportions with this, with this, with this, with this, not this. We could do it with this, with this, with this, with this. Like I could look at who's broken a bone. Categorical, exactly, Kayla, 100 points right there. Proportions deal with categorical data, so any of these red ones here work for proportions. To go and look at the proportions, we're going to go here to Analyze Distribution, and we're going to double-click the variable we want. There we go. And we're going to click OK, and then we're going to click the top red arrow and go to Stack. Then we're going to add in a little histogram options right here. You can do whatever you want. Preferably don't go too crazy, but add in account access, I would say. Nice and neat right there. And then we go over here, and we go to histogram color. I like adding my own color for it. And under the histogram color, we're going to go here and make it nice pink today. There we go. Perfect. Nice and beautiful. And so there we are with our histogram. Everything looks good. And we can see right here, there were 431 people who reported they have not broken a bone, 375 people who reported they have broken a bone. Now, when we make our confidence interval, we can go here to the red arrow again where all the options are at and make a 95% confidence interval. So this is telling us like, well, what is the true proportion of people who have broken a bone? We've got here 46% of our sample broke a bone, but for everybody, awesome, great job, Kayla, right there. You're welcome anytime. Have fun, good stuff right there. So we have here, this is how many people we see broke a bone in our sample, but what is the truth for everybody? Well, if this is a whole population, which is so interesting, this is really cool. You have different data. We see here that we're 95% confident the true proportion of people who have broken a bone, interpretation right there, is contained in the interval 43.1 to 49.97. Now, when we do tests right here, a statistical test can be done with a confidence interval. How? How do we do statistical tests with confidence intervals? How could you run a statistical test using a confidence interval? So how could you run a statistical test using a confidence interval? How could you run a statistical test using a confidence interval? So if you have a confidence interval right here, and you're looking at a value like 33, how could you test the value of 33 using your confidence interval? So using a confidence interval, how do we then say, well, let me look at my confidence interval and see if I reject or not reject the value? So you see how 33 right here is what? It's inside the interval. So that means we would what 33? What does this say right here? It says NR. What does that mean? At the 0.03 alpha, which is a 97% confidence interval, it's analogous to that, we would not reject 33 because 33 is inside the confidence interval. But look up here is the hypothesized value. So what can be hypothesized value? Does anyone know what a hypothesized value can be? Who has a guess in the chat for 100 points as we hop over back here to the main screen? What can a hypothesized value be? So this is the hypothesized mean right here. Like, could I hypothesize that 70% of UT students have broken a bone? Could I do that? So we don't have to do this portion, but this is how we could do it. We could go over here to test probability. I'm going to kind of close this down a little bit over here. But could I hypothesize that I think around 70% of UT has broken a bone? Now, I can tell you immediately, I know how this p-value is going to turn out because I saw the confidence intervals. If you remember from the confidence intervals, let's go look at that again. We'll put it all here on the main screen. I am 95% confident the true proportion of students who have broken a bone is somewhere between 43% to 49.9%. So I'm hypothesizing here that 70% of them have broken a bone. You'd say to me, Brian, wait, you think the truth is somewhere between 43 to right below 50%. So if you hypothesize 70%, which is any value you want to make up, you can guess any value. You can say like, I think this could be the truth. Someone would say to me, and let's look at it. They'd say, I reject that value. And you can see the p-value right there. They'd say, I reject the value of 70%. We have evidence against that. And we're rejecting the value. Why? We reject the value because it's not inside the interval. So with the value not being inside the interval, well, so you can kind of call it a hypothesis. So it's not really an educated guess. I would say good answer right there. Excellent work, Ariel. It's more off like your current belief. Think of it not quite like an educated guess, but think of it like a current belief, which could be an educated guess. An educated guess could be a current belief. Like, this is what I currently believe it is from my educated guess. So I'm going to throw another 100 points right there. I think educated guess is a good way to say it. And then we might say it's more of what we currently hold as true in our minds. Like, someone says to me, my friend thinks that 70% of UT has broken a bone. And I'd say, well, our interval right here suggests that we're 95% confident the true proportion of UT that's broken a bone is somewhere between 43 to 49%. Your friend's current hypothesis of 70% should be rejected because it's not contained in the interval. Now, this portion is not required there, but it's just showing that we could reject that. What if someone guessed, someone's like, I think about 44% of UT has broken a bone. Ariel, do you think we would reject the value of 44% of UT breaking a bone or not reject that value? So look at the interval right here and tell me, do you think using that interval that you would reject it at the 5% alpha? So if someone were to guess, like, maybe it's closer to, 45% of UT has broken a bone. So do you think you would reject that value or not reject that value? Looking at this interval right here, you'd say, well, it's somewhere, the true proportion of UT that was broken a bone is probably between 43.1 to 49.9. Your friend's like, I think it's probably about 45%. You'd say, well, I have to what that value because this. So would you reject that value or not reject that value, which means fail to reject? So looking at that value right there, you'd be like, well, that value, I have to do this to it. Your thoughts on that value of 45%? I'd look at that value and say, my friend, you know what? That value you just told me. I cannot this. What we say? Now that value is inside the interval. So since it's inside the interval, it seems like a possible truth. Well, so you'll kind of come up with your own, like your friend's saying to you, your friend's claiming to you, your friend's a medical student, they say, I think 45% of UT has broken a bone. So we would not reject this one because 45% is contained within the interval of possibilities, so the p-value is going to be high. Does that make sense? The p-value here is high, telling us that 45% is a possible truth. Observing 45% is possible given what we observed, like the truth of 45%, I should say. 45% being true is possible given our sample results. But compare that to the first test we ran where someone guessed 70%. Given our sample results right here, 70% is not very likely true. So your friend who said, I think 70% of UT is broken, and you're like, no. With what I observed, my interval tells me that I'm 95% confident that it's somewhere between 43 to 49%. The value of 70 is outside my interval of what I think is true. So you would reject this value right here. But your other friend said, well, I think it's 45%. You'd say, well, yeah, that's in my interval. So you see how 45 is contained in the interval, so we would not reject it. So anything inside the interval is a value we would not reject. Is this making sense here, Ariel? Like how we can use an interval to say like, well, here's what I think is true, like somewhere between this to this. And your friend's like, well, 45%. You're like, that could be true. Well, not accepted. So we wouldn't say we accept it. We would just say we can't reject it. I know it's kind of weird how statisticians talk. We don't use the word accept because that almost means like that is true. Like if I accept 45%, well, what if my friend were to say, but I think it could be 46%? 46% actually would also not be rejected. So let's go here. Another friend says 46%. And this is why we don't use the word accept, because if you use the word accept, it almost sounds like you're saying both of these are true. So 46% is possible, is likely, given what we saw. So the belief of 46% could not be rejected. Like if someone says, I think it's 46%, you would say, well, that seems possible, i.e. high p-value. Another friend says, I think it's 45%. You go, well, that seems possible. It's a high p-value. But then your friend says, I think it's 70%. You say, that doesn't really seem possible. You should reject that. You should think that that's no longer true. Does that make sense right here with your three friends? And this is why we don't use the wording. And great question right there, Gracie. We have one more lined up for this. We'll do that here second in a row. Your three friends right here, you would not be a 45%. Both of those are contained in the interval. But your friend who's like, I think it's 70%, you'd be like, our interval suggests to us that the truth is somewhere between 43 to 49. That number you quoted me, your current belief of 70%, is outside my estimate of what the truth is. I don't think, I think it's somewhere between 40. Yes. Yeah. So always say we either reject or we do not reject. A lot of statisticians will say fail to them all. I like to say I do not reject. It's just classical way is to say fail to reject. And you should know that because you'll hear it in disciplines. But we would not reject this, not reject that, and we could reject this one here. And you can use the confidence interval to do the test by looking at the value inside the confidence interval, i.e. this is not in the confidence interval, i.e. we reject 70. The other ones are inside. We cannot reject them, i.e. fail to reject. Great stuff right there. Ariel, excellent work. We're going to head over here. We got 2 questions lined up. We'll keep working away. Let's do this. Little chill music right here. Can we do C2? Yeah, Nathan, 3rd question of the row. Remind me, Nathan. We will do that. You got it. Which one's C2? C2, say. Right, I think we're writing some equations later. We'll write some equations. Canvas content is next. Let's do a version of the Canvas content number 10. Let's hop in, do some Canvas content number 10. Last Canvas content. We're on the last assignments for everything. Oh my gosh. Canvas content number 10. Oh no, I just closed down the chat. We don't want to do that. Canvas content number 10. We'll do one version of it here. Let's go check it out. So what do we have right here? First question is, side note, would it be possible to send a draft for a project? I give it a quick look over. Very quick. Can't promise I'll catch everything, but I give it a quick skim, and I tell you if I see any major errors. Because I could have over 700 students send me projects. So I give it a very quick skim. You're welcome. Thank you so much, Ariel. So I give it a very quick. I tell you if I see anything major. Can't promise I'll catch everything. Or else if I spend 1 minute grading each project, I'd spend 12 hours. 1 minute. And that's 1 minute in getting the project, replying. Yeah. So I'm very quick. Contingency table is a key component in understanding the chi-square test of independence. We just did one earlier, and guess what we get right over here? Oh, did we close it off? Let's go do it again. Chi-square test of independence is with 2 categorical variables. So we're looking here at 2 categorical variables. Please take a note if you're listening to me. Chi-square test of independence is with 2 categorical variables, and look what we get. Mosaic plot contingency table telling us if there is an association or if the 2 things are independent. Chi-square test of independence is seeing is somebody's label right here independent of their status, or is it not independent? And we do have evidence that there is a relationship, i.e. they're not independent. Check out the earlier version of this video where we went over this one step by step. This is about as true can be. The degrees of freedom for a chi-squared test of independence for the following data is 5. That's a weird way of asking it. So when we do degrees of freedom, this is a very simple formula for chi-squared. I'll explain with this. Here's how to, hey, Colin, thank you so much. I think I missed your last comment. I felt bad because I didn't say hi, but thank you, Colin, right there. Sending magical pixie dust from Disney. Now, this right here is a 2x2 table. Be very careful. A lot of people might use the totals right there, but don't use the totals. Here's the trick to figure out the degrees of freedom. So hopefully someone answers for 100 points. I'm going to give it like 30 seconds here. 2x2, you reduce and do 1 times 1. So what are the degrees of freedom? If this is a 2x2 table, which be careful, don't count the totals. We got here dead alive, we got here male, female. 2x2 reduced down 1 times 1, what are the degrees of freedom? These are easy test questions to answer if you know the formulas. And we even give it on the formula sheet. So 2x2 reduce down and do what? So what are the degrees of freedom? If this is a 2x2, reduce each one by 1. And what are the degrees of freedom? So 2x2 reduces to 1 times 1. What are the degrees of freedom? I'm putting 30 seconds on the clock right here. Quick way to memorize that formula. Who knows it right here? 2x2, reduce each one by 1. And what are the degrees of freedom? See if you can get it. Oh, I'm on top chat this whole time. 100 points in the chat. So if we have a 2x2, we delete 1 row, 1 column, and that's the degrees of freedom formula. So the degrees of freedom are going to be 2 times 2, remove 1 from each. 1. Degrees of freedom are 1. So what about this one over here? This is a 2. Now be careful. You might be saying, Brian, isn't that 3? No. That's where the mistake happens. When we do this, there are 2 levels. Don't include the totals. And there's 5 levels right here. So that is a 2 by 5. Reduce. We could do this one on our hands here. Reduce down. And there's the answer. There is the answer. So that reduces down to this. And that's the answer right there. Yeah. Oh, so we did one similar to that. And we can definitely do that. We got 2 more lined up before this. We can do that here in just a little bit. You got it. So this is the answer to the degrees of freedom. And so this is false. Very false right there. Chi-squareds, what's that saying? Chi-squared tests are used for hypothesis tests of the association between 2 categorical variables. Well, that's as true can be. We just saw that a moment ago. And we'll go over here and we'll take a look at it again. We have here 2 categorical variables, and that's a big thing. This is the count data condition. The count data condition. That's very true right there. You got it, NA, definitely. The sample size for each group must be the same for a 2-sample t-test. We did a question very similar to this earlier where we did a 2-sample t-test with not the same sample sizes. So the answer here is false. Especially when you look at the applets we're using. I don't think I have any of the applets up. You'll enter in different sample sizes sometimes for the groups. And we can see this. Oh, we could do a 2-sample t-test. 2-sample t-test right here. We could compare the average age of males and females right here. So comparing the average age of males and females, there's the age of people in stat 201 and the average age. And there is a difference. Males are on average older than females in stat 201. Yeah, we can do the company being sued. You got it. We got a lot of questions lined up, so we'll try to get to everything here. We see that the groups have different sizes in them, and this could be noted if we went and looked at this right here. The groups have different amounts. There's 451 females and 355 males, and so we are getting different sizes. So the correct hypothesis for a stat 201 false. Can you put the question here, Michaeli? Which of the following is not a requirement for the 2-sample t-test? So we always have randomization. We always have 10%. And then what happens here is we have to think about what kind of data are we working with. So success failure is only for categorical data. And so since 2-sample t-test is dealing with means, success failure is only when we're doing proportion stuff. Can you write the question out a little bit? Which is about the correct hypothesis for a stat 201 false survey. I'll try to find that one real quick right here. I'll try to find that. That is 10 out of 10. We got it right there. The correct hypothesis. The correct hypothesis. There's a p-value. Oh my gosh, it's mad at me for submitting forms. It said no. Really? Gotta go back and look at it. Let's go look at this right here. We got to preview it. The results of chi-squared. Calculate is not going to go backwards. Now lets me go backwards. I don't know what it's doing. Continuous table in chi-squared. What is the correct hypothesis? Cool. Okay. So what does the null have? This right here eliminates one of the choices. What does the null have? What does the null have? The null has this. This eliminates a choice. If we ever see something like this, we can eliminate choices and we can be very certain of it pretty quickly. The null has this. So what does the null always have? An equal sign. Michaela, great job right there. 100 points. Null has equal sign. That eliminates C. C is not a choice. So now we have to read the question. In stat 201, 39 had this, so we can confirm you can use different sample sizes. And we have assume that the conditions are met. Use the jump output loaded to answer the following question about the difference in the... So I think... Assume the conditions are met. Use jump output load to answer the following question about the differences and so on for these two groups. What are the correct hypotheses? So it looks like we're just testing for a difference because it gives no preference right here. Unless I'm missing it. I'm trying to read it over like 3 times. In the stat 201 fall semester survey, 39 students reported having this, whereas 56 reported having this. Social political views. Assume that the conditions to compare the 2 independent means are met. Use the jump out below to answer the following question about the differences in the stat 201 exam scores for these 2 groups, which are the correct hypotheses. So the null would be that they are equal, and the alternative would be that they are not equal. Gotta love how it randomizes those. That is not confusing in the least. And that's got it right there. Let's submit the quiz. We're going to get a 2 out of 10. That's all right, though. 2 out of 10. And the reason being is it does not imply any sort of greater than or less than. It's not saying that one group is bigger than another. So we'd use the does not equals alternatives. That makes sense, Michaeli, right there? It doesn't say, is this group higher than this group? It's just flat out, we're just looking to see if there is a difference. So that's how we would do it right there. We'd say there isn't a difference, and the alternative would be that there is a difference. You're welcome, McKaylee. Great job right here. Excellent. More chill music. Hey, that's some chill music. Hit it by accident, but that's a good accent right there. Let's see right here. I think the next question is... We did chapter 17. Let me see, McKaylee. There we go. And then next question comes from... Trying to see. Where's the next question? It might be... Essentially... Gracie has the next one. I think we're doing a 320 after that. Gracie said, could we go over a random poll? Which chapter is that, Gracie? Could you go over the next question? A random poll. It's on the homework. Random poll 700. I think that's chapter 16. I think that's chapter 16. Chapter 16, a random poll. Let's find this out. Chapter 16, a random poll. Chill music right here as we go find this. I believe this is chapter 16. Chapter 16, a random poll. Here we go. Here we go. Got the hiccups today. Random poll finds out. Let's find out what they found out. Let's do this. A random poll of 600 workers. Now, the number one thing you want to do when you get information is start marking what it is in notation. So we need to go here and immediately start marking the notation for this. I want to change the size of my dot. It won't let me. Oh, there it is. So let's go here and start marking our notation. And there is the pen, and let's do it. So 600 is going to be the sample size right here. That is our N. And then 11% is going to be what we saw in the sample. That is P hat. Now remember, P hat is what we observe in a sample. And if we know P hat is equal to 0.11, then Q hat is equal to 0.89. Those are complements. Whenever you get P hat, immediately find Q hat to solve for it right there. Next, we need to create a 95% confidence interval for the true proportion. And so we need to solve the equation P hat plus or minus a z-score, square root P hat times Q hat over N. And now we need to find the z-score. Now, the z-score is how confident we are. Like using a different z will change the confidence level. This z-score right here is going to be 1.96, but let's show that because 1.96 is the z-score for a 95% confidence interval, and it covers the middle 95% of the curve. So just by virtue of using the normal curve, we can cover 95% of the middle possibilities, and we'll see this here in a second, going to the David M. Lane applet. Mr. David M. Lane, MuBot's helping us out right here, and here is the David M. Lane applet. And we want to see the z-score for 95% covered. It's all over the screen right now. And let's go to 95% and do the between, and you can see the z-score right here of 1.96. So that z-score right there tells us what we'll be using for the percent confidence. Like 95% confidence equals a z-score of 1.96. If you have something different, make sure to put in like 90 or 99, whatever you're using, and you'll notice you cover more of the curve when you're more confident, i.e. a wider interval, i.e. a larger margin of error. So let's solve our numbers in here. We need to plug in the numbers now, and we're going to plug in 0.11 plus or minus 1.96 square root 0.11 times 0.89 over, and then we have 600. As long as we don't make any math error, which can happen, we should be good. I would solve for the margin of error first right here. Whoops. So 0.11 times 0.89 and divide by 600 square root. And so that is the standard error right there. It's a standard error. So this is the standard error times 1.96. That is the margin of error. So we have now found the margin of error is 0.025. At this point, I usually rewrite my interval right here to be the following. And this is basically the answer now. My interval now is 0. I don't have the pen. 0.11 plus or minus 0.025. And so now we are going to solve this out to plug in the numbers. And I'm going to disappear off the screen. And so let's solve it. There's the margin of error. And 0.11 plus. So 0.35 right there. And 0.11 minus. And there's the bottom right there, 0. So I am 95% confident the true proportion of people who have a second job to help pay bills of these working men is contained in the interval 8.5% to 13.5%. I'm 95% confident with this estimate of where the truth might be contained in. Yes, fantastic. What does the confidence interval say about the pundit's hypothesis? Because, and they hypothesized, what did they hypothesize? Ooh, this kind of relates to what we're doing. Because what? They hypothesized 8%. So because 8% is not in the interval, we would reject. We have strong evidence that more than 8% of working men have a second job. So it's the interval does not contain 8%, which literally goes to what we're doing in our project. Is a hypothesized value can be anything, but you'll see right here the value of 8% is not in the interval. So we have evidence that more than 8% because the interval is above it. So we would say we can reject that value of 8% and have evidence that more than 8% have a second job right here. We'll be coming back here in a moment. I think we're about to do the 320 question, doing some equations right here. I think that was next. Let's see right here. Nathan said, next question, getting it lined up. Here, we'll go to the main screen. We'll do this. And I think Nathan has the next one, 2C. Good stuff, Nathan, right there. Drop those questions. You're welcome, Gracie. Great work right there. Hopefully it's making sense right there as we follow through and work through some of these equations. Ask those questions if you got it. And great work, everybody. Just practicing and following along. Here we go with some 2C. Let's go check this out. So we got to write some equations here, I believe, because it says do the same. Write the implicit equation relating last amount to recent average account for houses in the rural setting. Feel free to only keep 2 numbers after the decimal. Cool. That makes life easier. So this is writing implicit lines by solving equations. We need to get our equations right here. And let's go make our line. M save into LM. So this is writing the linear model, saving it into the object M. We're predicting last amount, which is the Y variable. We're going to do it from recent average amount. And we need an interaction between, so let's put a count right here. And can I change what question I get? Yeah, of course, of course. I'll show how to write this equation real quick. And setting. And then this is the EX5, right? I keep trying to find it. Should be right there. Sorry. And then drop 1. Which one do you want to work on, Nathan? Let me know. Oh, I didn't do test equals F. I wish I just did default test equals F. There we go. Looks like it. Oh, I got to change my options around. Digits equals 7. SciPen equals 7. There we go. Looks. Ooh, what's going on with those digits? SciPen equals 5. Sure. A3 for the problem above, which is like the last one. So A3. Let's go look at A3. A3. Let me do a rethink right here. It's harder to find which question I work on when I do that. I'll have to remember later. I'll be like just showing like how to write an equation or something like that. Okay, so here we go. A3 is the question at hand. Let's go look at A3. So here we go. So right here, we're looking at question A3, and we want to know if the difference in strengths is statistically significant. So we're actually looking at the right plot right here. We have 2 models. And how could we know if the difference in strengths here is statistically significant? What would we look at in this output to help us know when you look at these lines, which are going to be pretty scrunched in the background right here? We'll make them not as scrunched. How could you look at these lines right here and know that the difference between their strengths, which is the difference in the slopes, is statistically significant? And do you see a p-value? Maybe yours looks like that. Look for my value on the screen. So is that the value? Which value are you talking about? Like, quote some more numbers on it. Your values could look similar to that. Maybe not. So the difference in strengths right here would be denoted by what? So that is the difference in the intercepts. This is a change to the intercepts, which is down here. Now, the difference in intercepts is statistically significant, but the difference in strengths is the change we see when someone... So the question specifically says, just want to double check, it says, is the difference in strengths. So this is, how does recent average amount get impacted by someone being a homeowner? So when someone is a homeowner, the relationship is weaker, and you see that here with the red line being a little bit lower. So this p-value right here is the statistical significance of the interaction. And we can also see this when we visualize the model. I think I don't have it stored right now. Let me store it. I think it'll run this, and it'll keep my code right there. Good. And then we run this right here, and the interaction has a strength of this right here. So it is the interaction. The interaction changes the strength of the relationship between recent average amount and last amount. So the p-value of the interaction would be a difference in strength. Does that make sense, Nathan? The p-value for the interaction tells us that there is a statistically significant difference in the strength of the homeowner no line and the homeowner yes line. And this is the change we see between the two of them, or the difference we see where homeowner yes has a less sloped line. And this change in the slope is probably not due to random chance. Now, what's really interesting is, do you know what the null hypothesis is for the coefficients, Nathan? The null hypothesis for all of these coefficients, which I want to bring this back to stat tool 1 here, because the null hypothesis for all of these coefficients is what? That any of these coefficients would be equal to what? This literally is a connection to stat tool 1 right here, because the null hypothesis for any coefficient in this model, and this is 320 stat tool 1 crossover, is the true coefficient for any coefficient in the model is equal to 0. And the alternative hypothesis is that any coefficient in the model is not equal to 0, that has a non-zero coefficient. And what do you notice about all of these intervals? None of these intervals do what? Which is why they're all statistically significant. 320 201 crossover right here. What do you notice about all those intervals right there? Hence why all the intervals are statistically significant, because we can reject the value of 0. I don't think any of those coefficients are equal to 0, because I'm trying to estimate with 95% confidence the coefficients. I don't think any of those coefficients are equal to 0. Why? So I reject 0. Hence, up here I'm saying I reject 0. Exactly. Do you see that? Hopefully a 201 student is seeing this, because this is the exact same thing we're doing in 201, where we look at the interval and we say, I think the true coefficient for this is here to here. Well, 0 is not in the interval. I reject 0. So we would say the null hypothesis is that any of these coefficients here, the intercept, any of these are equal to 0, but we have good reason to believe via the confidence intervals that they're not equal to 0. Also, when you do the test, you would reject the value of 0 because 0 is not contained in there. So really good kind of review and a crossover to what we're doing. This is the hypothesized value we use by default when we're testing coefficients. And then you would see it's on the interval. So it's like we reject it, which is all we're doing up here. So great stuff right there. Good practice. Great stuff. Let's head back to the main screen. Main screen. Awesome work. Next question. We've got 2 more lined up, so drop those questions if you got them. N8 has one, but I think we have one more for N8, right? Oh, maybe it's N8's next. So are we running out of questions again? No, we got like 30 minutes. N8 said, can we go over the hypothesized values? And I think, is that the last one? We did the working men. We're just flying through questions today. So we've got hypothesized values for T's. So let's go check out some hypothesized value for the T. And here we go. Let's go check it out. Of course, you got it, N8. Yeah, can you post a good bit of it, Hannah? Post a little bit of it. And give me... Oh, wait, we still have the bank... I think someone said the bank question. So, I'll take... No, drop the question. Tell me the number, Nathan, to make sure I see it. Let's go talk over that T-test right here. And because we got like 30 more minutes, or probably 25, I don't know. Go over a little snack before next class. 30 minutes. We got this. Here we go. Let's do the analyzed distribution right here. And we're doing a T-test. So we want to grab a quantitative variable. T-test, Mr. T is mean, if you're doing drugs. And we're going to grab a quantitative variable. We just did that one, Hannah. Check it out. We just did that one about 7 minutes ago. So we could circle back to if there's no questions, but we just did it like 7 minutes ago. So rewind the video a little bit. You can actually rewind live. And you'll see me work through it and solve the interval. So good stuff right there. We're going to grab a quantitative variable here. Like, let's look right here and do, how much do people sleep at night? Good question, right? How much do people sleep at night? And with how much people sleep at night, spread my graph on the T. My graph is symmetric, so I use them standard deviation and means. Well, so mine right here. So actually, we'll do one that's not symmetric. This might be more mean and standard deviation. Awesome, Hannah. Great work, Hannah. 100 points, Hannah, and everybody. Thank you so much. I go back and do questions, but I always try to like mix it up. Like I do ones, if we did it earlier the week, I'll usually redo it. But if we do it in the same video, I try to like mix it up in the video. Check this out right here. So N8, what would you use for this graphic right here? We probably want to write about 3 sentences right here. We're talking about how this is unimodal. It is not symmetric. It's very, very right skewed. So what would be the proper measure of center right here? The proper measure of center for this distribution is the what? Due to the extreme skew and high outliers here that people send 1,000 texts during class. I don't know if this is one class or what. but someone says they send 1,000 texts. So the center would be the median, and the spread would be the IQR. So the IQR right here, we could add it to the data if we want. If you're going to do the IQR, you could actually add it by going there to customize summary statistics and add it on right there. So the IQR is the measure of spread because it's how far is the middle 50% spread out. It's from 3 to 20, so it's 17. And then the median is going to be the middle or the 50th percentile. Now, I want to make this very clear. I think there are some people don't use enough words. They might just say the mean is this. You could say the average person sends 22.23 texts during class. Now, that's not the correct measure of center because this is skewed data. So I'd say the 50th percentile of students sends 8 texts during class. This is represented by the median. The spread of the middle 50% of students' texts during class, represented by the IQR, is 17. Do you see here when I'm saying the IQR is the spread of the middle 50% of students' texts? If I were to interpret the standard deviation, I would say the spread around the mean for the amount of text that students send is 63.24. Now, once again, what we pick here, so my spread for GPA is, that sounds like a very, very high spread for GPA. GPA wouldn't have a spread of 66.7 because GPA is on a scale of like 0 to 4. It shouldn't be a percent. Is it 0.667? So it wouldn't be a percent. That'd be 0.667 like GPA points. It wouldn't be a percent. So the spread is in units of the Y. Like this is a spread of text. Good questions right there, and 800 points. The standard deviation is not in a percentage unless Y is in a percent. So if you collect Y as a percent, then the standard deviation would be a percent. But so you're saying that, and I'll interpret it for you. The variation around the mean is represented by 0.667, which shows us how spread out the standard deviation of 0.667, which shows us how spread out people's GPAs generally are around the mean. The spread of people's GPAs around the mean is represented by the standard deviation, indicating to us that the variation around the mean is about 0.667. So don't just say the standard deviation is this, though. You don't want to say my standard deviation is 0.667. Make sure to include words like spread, and then standard deviation shows us variation around the mean. So it's probably good to say that's good questions right there. And then think about this. So here's the weird thing, is that we can actually use the empirical, not the empirical rule here. No, we can use not the empirical. Yeah, we can use the empirical rule. But due to the central limit theorem, we can use the empirical rule. So the central limit theorem states, and you might be like, no way. Let's go to the central limit theorem applet again. You know where we're going. It's our favorite thing. Central limit theorem applet. Because of the central limit theorem, it's called a theorem because it's something that is true mathematically. If we have very skewed data, and we could even make it more skewed, if we have very skewed data, but we have a large enough n, generally we want about 100, I would say. 25 is all the app goes up to. What we're looking right here is the distribution of the mean, not of a singular observation. So this is the average of 25 observations from a skewed distribution. Now, when we look at the distribution of the mean, which is what we're actually trying to talk about in these examples, the distribution of the mean will be more normal and tighter, and you see it right here. So because our sample size is large enough, we actually pass the nearly normal condition. You'd say, that's ridiculously skewed, Brian. And I'd say, well, the sample size is well more than 100. So we don't have to talk about conditions for this. You might say, well, we can't use a confidence interval. Well, we can, because it's the central limit theorem here allowing us to compare the distribution of the mean of this. So I'm 95% confident the true mean of the amount that students send of text during class is somewhere contained in the interval 17.8 to 26.6. And what does this mean right here? Well, to your question, N8, what if somebody told me they think the true value of what people send during class is 30 texts? If you were to say 30 texts is what I think people send, so we'll make this interval kind of a classic way right here. If you were to tell me you think the truth, here's the classic way right there. I would take a picture of this. If you said, I think the truth is people send 30 texts. So it's any value you want. Someone says, I think people send 30 texts a day during class. And I'm like, that's what they hypothesized. They just made up that value. A hypothesized value can be any value you want. It's whatever you believe is true. Someone says, I think it's true 30. So what would you tell them about that value of 30? So what would you tell them? Someone says, I think students have a texting problem. They send like 30 texts during class. And I'd say, what that value? I think the truth. I'm 95% confident the true mean, almost said the wrong word. I'm 95% confident the true mean amount of text that students send during class is somewhere contained in the interval 17.8 to 26.6. So that value of 30 you just told me is what? It's outside my interval. So I what that value. So finish my sentence. I what your value of 30 you just gave me. And I'll show you the way of doing it. You don't have to do this, but it shows that we would do this. If we had over here somebody claiming 30, we could test that value of 30. And then the value of 30, because N8 said it's outside the interval, that value of 30, we would definitely what? We'd reject it. Another friend says to you, I think 22. I think students send about, 20. I say 20. You say, well, you told me two values right there. You told me 20 and 22. Well, that value of 22, guess what? We would not reject it. There's the p-value for the two-sided test. I would not reject 22. And so you're saying, wait, so that's true? No, it's not that that's true. It's not that that's true that students send 22 texts during class. Just like 20, it's a value I do not reject. So any value inside the interval I do not reject. Notice how 20 and 22, these hypothesized values. So I need to write up a hypothesized value and value to reject. Basically, what we're doing right here. So walk through the steps, explain why you're hypothesizing this value. You need to talk about why it's important to your company, like why you're hypothesizing this value, what it means to your company, and then look to the interval telling you whether that hypothesized value is going to be a value that is true or not true. Like, I shouldn't say true or not true, a value that we would reject or not reject. So could this value be believed or not be believed? The value of 20 is a possible true value. We could believe it. The value of 22 is possibly true too. Not saying it is true. It's just possible. Sure, that's believable. But the value of 30 is not believable. Awesome. Great job there, N8. Excellent work. We'll head back to the main screen. That's how we can hypothesize values. Good stuff. Great questions. That's how we can see, is a value true? Well, let's run a test to see if we believe it. We don't really say things are true in statistics. We say, do I currently believe this? Should I reject this belief? Should I hang on to this belief? And that's what it means to not reject something. To not reject means, yeah, I'll continue to believe it. That's possible. Possible, given what I saw. I think Nathan had a question. Nathan's question was... And then Nate, thank you so much. All those questions right there. 100 points in the chat. I'll take the very last question. So Nathan was wondering about 2C. Oh, did we have another one? I swear someone wanted... We've done... If you saw a question we didn't do, let me know. 2C. Let's go look at some 2C for some 320. So if you have a question, drop it in, because we're running low on questions. Let's go look at some 2C for 320. Here we go. Is there a statistically significant relationship between the probability of donating and the donor's age? Very last one, you got it. Is the relationship strong? Have practical significance? Take the relationship to be strong. If to donate varies by more than 20% to the range of the data, examine the results with the visualized model to get your answer. Yeah. Campbell, yeah, ask questions. Feel free. Let me put it. Awesome. I'll put this in the chat. Awesome. Ask questions if you have them. I can see the chat in real time. Thank you so much, Campbell. 100 points, Campbell, to get some free points in the chat right there. And thank you so much, Campbell. Following along right there, pausing the video. That's a great thing to do right there. A lot of people like that feature that we have on YouTube. So, it's, once again, I think it's like if someone told you this, but then you might get behind or something, you like to catch up. But still, I think that's a great feature we have because I do talk quickly sometimes. Maybe. Okay. So we need to make a model right here. We worked a few questions. A lot of help for this assignment. A lot of help. So let's go here to the probability of donating. Nathan, I'm going to make some errors right here. Nathan, I want you to call out my errors. 100 point each error, Nathan. Nathan, I want you to call out each error. It's relationship between all donating. It's relationship strong. Okay. Nathan, I've got some errors. What's the data set we're using? Nope. Nope. We got some errors. Errors. Problems. What do we got? 100 points each problem right here. Someone's going to run into this and be like, what? Got some problems. Our linear model. Linear. We got problems. GLM family binomial. So it's 200 points, right? Quick right there. Reason being, we're predicting a categorical Y, whether or not someone donates. So we have to do generalized linear model. And then we're going to add here an extra argument I like to do on a separate line. Family equals binomial. And there we go right there. Let's go to the summary. Well, let's visualize it. And let's take a look. Ooh. Ooh. What do you notice about everyone donating? Yeah, let's do the family being sued. Is it family being sued? I think it's a company, right? I think it's a company. Campbell, correct me if I'm wrong. It's a company, I believe. A company being sued. Let's do that one next here. I think someone wanted that one earlier. What do you notice about anyone donating right here? We can look at the confusion matrix for this. We can actually find out what about this model. What does this model do for anyone donating? Which is actually the naive model. What does the model do for anyone donating? Company, yeah. Awesome. We'll do that one next, Campbell. You got it. Thank you, Campbell. 100 points, Campbell. No one will donate. The model says no one will donate. So we could plug into the model right here. And here's a thing we don't usually do. Let's go here and go to the model and go to... We're predicting based on someone's age. So we need to make a data frame right here. Data.frame. Oh my gosh. Where's my data frame? There we go. Data.frame. And did dplyr take that over? No, it's base R. Good. And I'm going to go here to age equals the lowest person's age, probably like 18. Highest person's age is 100. And then we're going to go here to predict using our model, new data equals data frame, and type equals response. And what do you notice? What do you notice about a person who is 18 years old, which you can see it right here? That's about where 18 is at, hence it graphs to right here. Let's kind of associate these by drawing on the screen a little bit here. If you notice, the 18-year-old person is the first person I made predictions for, and they would be right here. The 100-year-old person, pretty much as old as they get, is this person. Here's their probability, and that would be all the way over here. So what do you think, Nathan, about this when you look at the differences between these two right here? And we could actually find it mathematically if we really want. We go here to predict 2 and minus. We're just going to take these 2. And we take right here and do this. And we get the differences. So that's the difference between these. We've now solved for the difference between an 18-year-old's probability and a 100-year-old's probability. Because this was the second person's probability. And this was the first person's. And we're just seeing what is the difference. We could go crazy right here and say, okay, well, maybe people at 0 could donate up to 120, like oldest person. And we're only getting differences of this. Yeah, so it is statistically significant. Very good job right there. It is statistically significant. And the p-value right here is, be careful, the p-value, you might have the decimals a little bit different. So remember, p-values, can, this is a good thing, Nathan, 100 points. P-values can only be between what and what. P-values, since they're probabilities, can only be between what and what. Mine's a little bit scientific notation different than yours. Always remember this, because you ever say p-value of 4.36, I'll be like, p-values can only be between this, because they're probabilities. 100 points online right here. P-values can only be between this. Yeah, you know, yeah, you got 100 points right there. They can only be between 0 and 1s. Oh, Campbell. You got it, Campbell. If you got another question, let me know. We can do it still. We can do the company being sued. It's a good tricky one. It's a good type 1, type 2 error question. You got it, Campbell. No, I like working problems here. I try to do as many new ones as we can, but no, like, if we haven't done it today, then we did it yesterday, but that's fine. No, Campbell, keep it up. Campbell, I want to say 500 points. No, I really like that. I want people here asking as many questions as they can, but I also like that people use the old videos because, you know, we try to do as much as we can. And I want as many people to hop in and ask questions. But Campbell, that 500 points goes out to you right there. If you still want me to work it live, I can work it live and explain through it. So we still got 15 minutes. So we don't have any questions. So Nathan, I might, because I've done a lot of the assignment. Why do we know it's statistically significant? Why do we know? Whenever you hear statistical significance, what do you think of? Like, you hear statistical significance, it means you better check this. Oh, you're totally fine. Don't worry about it. You can always ask me to... Is there a sale on Pokemon Go storage? Oh, they just increased it. Whenever you hear statistical significance, you should think what? You hear statistical significance, 201, 320, 474, 475, you think, I need to look at this. Statistical significance, I'd better go look at this real quickly. If I hear statistical significance, I'm like, better go look at this of it. So whenever we hear statistical significance, we're always going to say, let's go look at this. What do we think? P-value right there, 100 points. You know it. P-value. Boom. P-value. Statistical significance means a p-value less than 0.05. So The way in which age enters into this model, it brings with it new information not accounted for by random chance, or unlikely by random chance, I should say. So it is doing something beneficial, but interestingly enough, once again, it doesn't do any better than the naive, which is the majority level. And that's what it's pointing out for us here in this output, is that the predictions of the model right here predicts everybody no. Everybody's predicted no, which is the majority level. Most people are not donating. We could also find this by going here to a table. You can see the naive model with a table of your Y variable. We're going to go to donate, and this is the same naive model. So any naive model just says, what are most people? Most people are this. Predict everybody's this. That's how the naive model works. Predicts everybody is the majority level. That's got it. So remember what the naive model is. Now, this is the naive model for categorical Ys. Categorical Ys are when we're predicting, at least in this instance, a 2-level logistic, like binomial. And yeah, we're predicting if someone donates yes, and it has level yes, no. Yes is the level of interest because it's last. Well, what questions are there? We still got like 14 minutes. I'm going to send that announcement to the last class of the day. Oh my gosh, today's almost over. Last full week. 2 days of the class. Course project. Good. Awesome stuff. Okay. Go. Let's go send out that email. A little chill music. We got this new song, which I'm overplaying now. It's the way we roll right there with new music. Let's go right here. 475. And let's go send the announcement. Brain jumped. We are so far along. Class in 27 minutes. Big bonus. See you soon. Click here. There we go. Class link is sending out. Well, might be it. If you have any questions, let us know. I might grab some food here real quick. Got a little bit of time between classes. Might end a little bit early today. Almost class time. Last class of the day. Time flies by. Well, with that, I think we're done with questions. So we got through all the questions. A lot of great stuff in this video. We got some 201, some 320. We did some time series earlier today. We did the project. Great stuff. Until then, we'll be back tomorrow. Email me if you have questions. Discord, I'll hop on there. Trying to answer everything we can. We got this. Bye for now, everyone. Bye.